So both our count vectorizer and our hashing vectorizer are going to generate raw counts. The raw counts of all the terms of all the words in our documents, across all our documents. Now let's consider using raw counts. Do you think using raw counts is a good thing? It's some way we can generate a feature matrix for a machine learning model to use. So we could use the output of these vectorizers, either the hashing or count vectorizer, to train a machine learning model to do some task, to do some prediction task. But do you think it's in a good state at the moment? Do you think it would be, what are some problems with just using the raw counts? Well, there's several problems with using raw counts. First off, these documents are going to vary widely in their size and how long these documents are. Remember, when we say documents, we don't refer to our everyday use of the word document, but here document is an observation. Certain documents might be just 5 words, others might be 20 or perhaps even 100 if it's a very long sentence. In this case, we set sentences to be our documents. So we have the problem with the length of these documents. That's one problem. Let's consider common words. Common words like the and is. Those words are going to have a very large count. But we understand that these words aren't going to be very important. Would you agree that counting words like the and is, including them in our count matrix, do you think they're going to add much predictive ability? Do you think there is much signal in including words like the and is, or counting those words, or having these words have a very strong count, a very large count? No, these words like the and is aren't going to be very helpful for a classifier in this case, or whatever we're trying to train. We understand like the word the and is are going to be found throughout our documents and aren't going to be parentially found in one document type over the other. And those words might have a large count and might overcrowd or overpower the more important count, the more words that are more important. So we have two problems here. We have the idea that documents are going to vary widely in size, so we got to consider that. We also got to consider some sort of weighting scheme. Some sort of scheme that's going to preferentially weight certain words that we believe are going to be more important over other words that we understand aren't going to be as important. So this can be solved, this problem can be solved by using the term frequency inverse document. It's going to be a popular weighting scheme to improve the simple count based upon the bag of words model. Now it's a product of two values, the term frequency and the inverse document frequency. Now this weighting scheme, or this transformation process we can apply to our counts, has different variations. There's different variations. We're just going to focus on one common one, but keep in mind you can play around with these variations for your task. Let's talk about that term frequency. What we're going to do here is that the term frequency represents how frequent was that term across the document. So it's going to be equal to the count of that word over the sum of squares of all the counts. Divided by the square root of the sum of square of all the counts. So essentially you can view that each of our documents is a vector. You can view each document as a vector with multiple dimensions, a p-dimensional space. So each word in the document, or each word that we are counting, is a dimension. So we're simply normalizing this vector so it can have a unit length of 1. So we're going to normalize all our documents to have the same length. And this will fix any problems of documents that are very long compared to documents that are very short. Set them all to have the same length. So in other words, if I can just illustrate it here, let's say we have a very short document that has 1 there, 0, 0, and since there'd be a lot of zeros, and then 2, and then 1, and then 3. So this document is very short, only 4 words, and what we got to do is we got to go ahead and, let's go ahead and calculate the length of this document. So we have 1 squared plus 2 squared plus 2 squared plus 1 squared plus 3 squared. So if I do the math, so that should be 1 plus, that's 5, that's 9, that's 10, and that's 19. So if I did my math right, this should be a value of 19. So then the square root of 19, whatever that number is, I'm just going to write that out, square root of 19. So we're going to normalize the counts such that we have 1 over the square root of 19, 0, 0, 0, so forth. Then we encounter a non-zero term. We divide by the square root of 19. So now this vector, this row, has been normalized. And of course you apply this process for all the documents across our corpus. So that's the term frequency. So we've taken our raw counts and we generated term frequencies. Now let's investigate that other term here, this term frequency, inverse document frequency. So what we have to do now is for each word that we're counting, we have to generate what is its document frequency. How frequent is it across our entire corpus? And going back here, the reason we're doing this is because we want to go ahead and amplify the signal of important words and reduce the volume of words that aren't very important. Words like the and is, they're going to have a very large count because they're very frequent, but we understand that they're rather noise. We can view them as noise in our data. So what we want to do here is that ideally we want words that perhaps aren't very common throughout their entire corpus. In general, they're not very common. But when they do appear, they tend to appear more frequently in one type of document over the other. For example, a word like, let's say the word tree. Say the word tree. And let's say this word isn't very frequent across the documents we're working with. But when it does appear, let's assume it mostly appears in documents referring to Python the animal. So we want to boost that word's contribution. We want to boost that signal. So you want to increase the weight. So we're going to increase that count. So we're going to upweight it. Words like the, which are common throughout our corpus, we want to reduce that count. Drop that volume down to not 0, but kind of a small value. Reduce its contribution to the data set. So let's define the inverse document frequency. And so in this case, each word is going to have a IDF score. And that's going to be equal to the number of documents in the corpus, so the size of our corpus, over 1 plus the number of documents with term t. So in other words, let's say, I think roughly speaking, we have around 500 documents. So let's just assume that, 500 documents. And we have, in those documents, let's say close to 400 of those. 400 of those contain the word the. So the inverse document frequency will be 500 over 400 plus 1. And since we're going to deal with large values, it's customary that we take the natural log of this inverse document frequency. So we're going to take the natural log of 500 over 400 plus 1. So considering this definition of the inverse document frequency, what happens if a word is found throughout our entire corpus? It appears in every document in our corpus. What would be its corresponding IDF score? So if it appears in every document in our corpus, then we're going to take the natural log of a number that's very close to 1. A number that's very close to 1, we take the natural log of that, will be a number very close to 0. So notice its IDF score for that word will be 0, which makes sense. Is this going to achieve what we wanted to do originally? Words that are very common throughout a corpus, we understand aren't going to contribute much. We want to reduce that volume. So its IDF score will be very small. We're going to reduce its contribution. On the other hand, if a word is very rare, then we're going to take the natural log. And here, a very large number. So its IDF score will be large. So we're going to weight its count. We're going to boost its signal. You might be wondering, what is the +1 in the denominator? Well, the +1 in the denominator is to avoid situations in which a word doesn't appear at all in the entire corpus. So we want to just avoid a situation where we divide by 0. So that's why the +1 is there. So once we generated term frequencies for each row, for each document, for each observation, then what we're going to do is that for each individual word, we'll multiply its term frequency by its IDF score. So that product of the term frequency and the IDF score is what is called the TF-IDF value. So going back here, I know it's getting a bit messy. So here we take 1 over square root of 19 and multiply by this word's IDF score. So each word is going to have a different IDF score. So 2 over square root of 19 times whatever this column is, times its IDF score. I'm going to say, I don't know, let's call it column 500, and so forth. So essentially what we're doing here is that we're re-weighting our counts. We're taking our raw counts. We understand that using these raw counts are only so good. Let's improve on the process. Let's go ahead and fix the problem of various document sizes. That's where term frequency comes into play. Let's go ahead and reduce the volume of words that are very common throughout a corpus, because that's pretty much noise. They're not going to contribute much. They're not going to contribute much pattern, much structure for a machine learning model to exploit. So when we reduce its contribution, that's where the inverse document frequency is going to come into play. So with this inverse document frequency, the term frequency, inverse document frequency, let's go ahead and see how we can do this in scikit-learn. So in scikit-learn, there's 2 ways to do this. Let's explore one way. There's a TF-IDF transformer, and the way that this works here is that you have to give it the array of your documents, the array of text, the array of strings. And when we use this TF-IDF transformer, it's going to encompass both the counting process and the transformation process to go into TF-IDF weights. So let me just erase this here. Sorry, I misspoke. The TF-IDF transformer is going to take a counting matrix and generate the TF-IDF weights. Let me go ahead and write it out here. Let me go sketch it out. Here's our workflow. We have our data. We have our spacey step where we take our text and generate documents. I'm just going to call this maybe just D for generating the documents. Let me just D OK for doc. Then here is the bag of words model. BOW. X of T, I'm going to call this X of double T. Then here is our TF-IDF. So right here, this is a count matrix. So that's what the transformer is going to do. As input, it's going to accept the counting matrix. So let's go ahead and look at that in scikit-learn. So we're going to import the TF-IDF transformer. Let's create the object from that class. And we use the fit and transform method, and we pass it the word counts. This was the output of the bag of words model that we saw before. Let's print out the weights, and there it is. So anything you observe that's interesting? or that it's expected given what we talked about? Well, since we're dividing by, square root of a sum of a number and some score, we'd expect that the output of this transformer, our counts, are no longer going to be integers. They're going to be fractional numbers, right? They're going to be floats. So we moved away from raw counts, and now we have the TF-IDF. So this is a TF-IDF value for all the values, for all the non-zero values in our count matrix. It's no longer calling it the count matrix. I'm going to call it the TF-IDF weights matrix. So once again, we have a sparse matrix, but we moved away from raw counts. Note, there is a different variation of TF-IDF, and that's called the TF-IDF vectorizer. And the only difference between the vectorizer and the transformer is that the vectorizer just combines these two steps here. So the vectorizer is just going to automatically do the counting process and then generating those counts into TF-IDF. So don't get too confused there. Where we have the transformer and the vectorizer is just, they only differ. It's the same algorithm underneath the hood. The only difference is that the TF-IDF vectorizer has both steps. It has the step where it takes the array of strings, generates a counting matrix, and taking that counting matrix and generate the TF-IDF matrix. The TF-IDF transformer is going to accept a counting matrix as its input. So if you're deciding which one to use, well, what is your input? Do you have counts, or do you have an array of strings? And of course, we can look at the documentation. We can go ahead and further inspect the difference between the two, but the same algorithm underneath the hood. It's just, to reinforce again, vectorizer has those two steps all combined in one transformer. One thing that might be interest is, let's look at those IDF scores. You might be wondering, what are those IDF scores? We can look them up. So after we've trained our transformer, there is an attribute called IDF underscore, which will return to us the IDF scores. So let's say we want to look at the top IDF values. So which words had a strong weight, had a very large weight for IDF? So that's what we're going to do here. We're going to use the arg_sort method. So this is going to return the indices that we can use to sort our matrix, our array of values, our IDF scores. We want the highest rate to the lowest weights. Let's look at the top 20 weights. Let's get the feature, so let's get the mapping between index to word. So what we're going to do is we're going to look at the indices that had the largest IDF score, use the mapping between the index to word to figure out which words had a strong, a very large IDF weight. We're going to print those out, print the top 20. So these is the output. So in general, what this is describing here are words that are not very common throughout our corpus. So they have very low document frequency, so that their contribution to the counting matrix will be upscaled, will be upweighted. So this means that even though MicroPython doesn't appear very often, when it does, its score will be boosted. So this will hopefully help out our classifier to boost the signal, reduce the noise, and make more use of the patterns in our data set. One last thing I want to talk about the TF-IDF, but generating these IDF weights is going to render our process stateful. So we could have, if in our workflow, if we had used a hashing vectorizer for the bag of words model, and if we combined it with the TF-IDF transformer, what's going to happen is that now we have a stateful process. Because in order to calculate the IDF weights, I need to know the document frequencies for all the words. So I need to keep track of all those interactions. So I lost that stateless property.